Okay, to question 14. Right, question 14, we have this a piece of ruler that is uh, secured in the bench end, and then you put a piece of cardboard. Then you allow it to oscillate in the vertical direction. The variation with time of the displacement is shown there, of the cut of the ruler. Okay, so it looks like a sine curve, but obviously it's decreasing. So the student claims that a curve can be represented by the equation. So identify two features which is wrong. Okay, this graph is a pure sine curve, but the graph is actually a cosine graph. Okay, so one thing is cosine is not sine, is not sine, but not sine, not sine graph, because sine graph starts from zero. Okay, the sine starts from 0, from y equals 0 at t equals 0. Okay, so this is wrong. The second thing is the amplitude. If you look here, the amplitude decreases. The amplitude decreases. So actually there is a damping, but this question, this formula here says the amplitude is constant. So again, this is not correct. So the amplitude decreases. The actual amplitude decreases, uh, which is not not uh, uh, not given, not shown in the question, not shown in the equation. Okay. Uh, Now, in reality, there should be some kind of exponential decay term here. You don't have to know this, but you just know that this equation tells you that is a sine curve and the amplitude is constant. Okay, but in reality, this graph acts as a decreasing amplitude. So this is not correct. Okay, next part there. Use the graph here to find the angular frequency of the angular frequency, omega. So omega equals to 2 pi over t, right? T is the time taken for one oscillation, one cycle. So if you look at the graph, T is one cycle is from here to there. This one T. So T is 1.5 seconds. So you put that 1.5 second inside, you'll get the answer. And that's 4.19, 4.19 radian per second. What about the acceleration at T equals to 1.5 second? 1.5 second. At t equals 1.5 second. So what we need to do is make use of the definition for acceleration, minus omega squared x. No, at x equals to 1.5, what is the value of the displacement? If you read from here, the value of displacement at 1.5 second is 2.2, right? 2.2. Okay. So x equals to 2.2 at t equals 1.5. So you substitute that value inside, omega already obtained earlier, and multiply by 2.2, and 2.2 is from the graph here, 2.2 cm. You may want to convert it to, so if you work out the value, you should get minus 38.6 cm per second, because we use cm per second squared. Okay, now next part, the cut is now replaced with one having a large surface area. Now, the cut here is actually trying to increase the air resistance. So if we have a larger surface area, means that the air resistance become larger, so because surface area. So you actually expect uh, the damping to be larger. When the damping is larger, so you ask to draw a graph, another graph to show the effect. Uh, so to draw another graph, okay, let me just change the color. Change away. So you expect, what you expect is that when the larger damping, you actually expect the amplitude to decrease faster. Okay, so you can draw a graph that shows a more rapid decrease in the amplitude of vibration. Okay, so this is how you uh, of course, the timing, the point where it crosses zero, you can draw them to be about the same or a little bit larger also. It should be fine. Okay, so this point will intersect zero. This shows you the what do you call the period, whether it's being increased. You can draw a little bit, you can draw it to be the same or a little bit larger, it doesn't matter. Okay. So the effect of larger surface area is to introduce a larger air resistance or larger damping force.